In this chunk, we're going to talk about taking a probabilistic approach to clustering, and that will solve some of the limitations of the k-means algorithm. The way we're going to go about this is, in this particular chunk, we're going to talk about the general approach and the probabilistic model that we're going to use, and then subsequent chunks will talk about how to do learning and inference in that model in order to actually solve the clustering problem. So this is all about, to start with, our assumptions we're going to make about the data. And we're going to attempt to write down a little probabilistic recipe for generating the data that has the notion of clustering built into it. The generative model is going to work as follows. That's what's shown on the right-hand side of this screen. And on the left-hand side, I have a little schematic that's going to show how the probabilistic recipe works. Okay, so the way we're going to generate the data points is each one is going to be generated IID. So we're going to cycle through them in a loop and draw them all from the same generative process. In order to build in the idea of clustering, we're going to introduce a latent variable. And the latent variable, we're going to call it S, as it's going to play an exactly same or similar role to the idea of the assignment variables in the k-means algorithm. So S is going to be a latent variable which is not directly accessible to us, which takes one of k possible values. And in order to generate that discrete latent variable, we're going to sample it from a categorical distribution. So this is a categorical distribution here. So the pi k's in here, this parameter pi k, in general, I should say theta are going to be our parameters of our model, and that's going to include these pi k's. So pi k's, there's going to be one of them for each one of our discrete settings of our variable, and it'll just indicates the probability of coming from that cluster a priori. So notice that these things have to sum up to 1. So in the case on the left-hand side, a setting for pi might have pi 1 equal to a half, say. So the 50% chance of coming from this cluster down here. Pi 2 might equal a quarter. So there's a 25% chance of a randomly chosen data point coming from this cluster. And pi 3 says that there's also a 25% chance of coming from this cluster if we pick a random data point. These things clearly sum up to 1. Okay, so there's a categorical distribution over this latent variable S. And once we have that latent variable, so the latent variable is going to play the same role as the cluster membership variable before. It tells us which one of these k clusters we come from, k being 3 in this example. Once we know which cluster each data point comes from, we can then sample the actual observed data value. And the way we do that is, in this very simple model, we're going to assume our clusters have a Gaussian shape. So we're going to sample the observed variable. These are our x's, if you remember back to the k-means algorithm. We're going to sample this knowing which cluster each data point comes from. And we're going to sample it from a Gaussian distribution in X with a particular mean parameter and a particular covariance matrix. And there's going to be a different one in general for each one of our k clusters. And that's what is shown on the left-hand side by these contours. So this middle cluster, this second cluster here, has a mean which is shown by this dot in the middle, and then it has a covariance matrix sigma 2 that might look something like, say, it would have diagonal elements here, sorry, off diagonal elements which are set to 0, and on diagonal elements which maybe was equal to 3 squared and maybe 1. So because it has a narrower height than it does a width. And that's what's shown on the diagonal here. In general, these covariance matrices can be correlated. So in that way, by having different covariance matrices attached to different clusters, we can hope to deal with this issue of handling clusters with different shapes in different parts of the space. And the MK here are going to play a similar role when it comes to learning as the means in the k-means algorithm. So we've got something which looks a bit like the means or cluster centers in the k-means algorithm. And we've got this extra bit which will help us handle clusters which are different shapes. Good. Okay, so that's the generative model. Data point comes in, sample the cluster membership, then you sample the actual observed variable x from a Gaussian with the mean and the covariance that the cluster it's assigned to has. And that's our toy recipe for how data is generated. That's our assumptions about the way the data we're looking at was generated in the first place. And once we've built that model, so here's an example of some data we'd actually get from that model. The colored circles correspond to data points that were generated from the model that we just talked about. And the way we're going to use that model to do clustering is we're going to perform sort of two steps conceptually. First off, we're going to learn the parameters from the data using maximum likelihood. Let me just recapitulate what those parameters were. So they were the pi k's. That's only part of the parameters. The other parameters are these things in here. So we need to incorporate the means, or the cluster centers, MK, and the covariance matrices. And we have one of each of these for all of our k equals 1 through to big K clusters. So we're going to, in our first step, estimate the parameters from data. And those parameters, we could estimate in multiple different ways. We're going to assume that we're going to use maximum likelihood learning to do that. Okay, we're going to assume we've got bags of data, and so perhaps maximum likelihood learning is a sensible thing to do. We don't need to retain uncertainty in our parameters. There are algorithms that do that, but we're not going to talk about them for the minute. We'll actually come back to that at the end. So we're going to estimate our parameters, the pi's, the mu's, and the sigmas from data. And then having estimated those, we can then run through each of our data points and say, given the estimated parameters, these are ML, and the actual observation, xn, how likely it is we come from each one of the clusters. So that sort of intuitive would look like this. We consider a point, say this one, and we compute what's the probability it came from cluster 1. Well, that's obviously going to be quite likely because it's quite near to cluster 1. What's the probability it came from cluster 2? That's going to be a bit less likely, but still have some probability. And what's the probability it comes from cluster 3? Well, that's going to be even more unlikely because it's miles away. But we can compute that using Bayes' rule. Okay, and that will then give us a soft way of clustering these data points because it will be probabilistic. So it won't be, a hard assignment to cluster 1. It will say, with 99% probability it comes from cluster 1, but there's a 1% chance it comes from cluster 2, and the next to 0 chance it comes from cluster 3. So both of these steps, the use of having covariance matrices to model clusters of different shapes, and the method for performing inference to give us soft clusterings, will solve two of the problems that we identified with the k-means algorithm. Great. In the next chunk, we're just going to have a very short chunk, which is just going to ask a question about the mixture of Gaussian's generative model to make sure that we're happy with it.